In previous lecture, I already discussed simple graph, multigraph, pseudograph, directed simple graph, directed multigraph and mixed graph. Today I will discuss adjacent and degree. First definition about adjacent, definition 3. Two vertices U and V in an undirected graph G are called adjacent or neighbors in G if U and V are endpoint of an edge E of G. Such an edge E called as incident with the vertices U and V, and E is said to connect U and V. In simple way, you can say if there is a edge E between U and V, then U and V are adjacent, or you can say E connects U and V. Suppose this is a edge E, this is U, this is V, then U is adjacent to V, V is adjacent to U, and E connects U and V. Next definition 4, it's about degree. The degree of a vertex in an undirected graph is the number of edges incident with it, except that a loop at a vertex contributes twice to the degree of that vertex. The degree of vertex V is denoted by DEG-V. So how many edges are incident on that vertex is called its degree. In loop count as degree 2. Next definition 5, it's about neighborhood. The set of all neighbors of vertex B in graph G equals to VE denoted by NV is called the neighborhood of B. If A is a subset of V, we denote by NA the set of all vertices in G that are adjacent to at least one vertex in A. So N of A equals to union of B belongs to A, N of B. If A is a subset of B, then all the vertex which are adjacent to at least one vertex of A called as neighborhood of A. Let's say some examples that you can understand. Now example 1, what are the degree and neighborhood of the vertices in the graph G and H? We have two graphs, one is G, another is H, and we will find the degree and neighborhood of each vertex. Now start with graph G. For vertex A, degree is 2. Due to these two edges, it's adjacent to B and F. For B, degree is 4. B is adjacent to A, F, E and C. For C, degree is 4. For D, degree is 1. For E, degree is 3. For F, degree is 4. For G, degree is 0 as it is not adjacent with any other vertex. Next, we will find the neighborhood. Neighborhood of A are B and F. So N of A equals to B, F, then N of B. Neighborhood of B are A, F, E and C. Neighborhood of C are B, F, E, D. Next, neighborhood of D. Neighborhood of D is C. Neighborhood of E is F, B, C. Neighborhood of G is 5 as it is not adjacent with any other vertex. Next we will find degree and neighborhood for graph H. Now for A, degree is 4. It have 4 adjacent. For B, degree is 1, 2, 3, 4 and this loop count as 2. So it's 6. For C, degree is 1. For D, 1, 2, 3, 4, 5. For E, 1, 2, 3, 4, 5, 6. Next we will find neighborhood. Neighborhood of A are B, D and E. The neighborhood of B are C, D, E, A and B itself as there is a self loop to B. The neighborhood of C are B. The neighborhood of D is E, A, B. The neighborhood of E is D, B, A. So these are the neighborhood. Neighborhood of A are B, D, E. Neighborhood of B are A, B, C, D, E. B included as there is a self loop. Neighborhood of C is B, neighborhood of D are A, B, E, and neighborhood of A are A, B, D. A vertex with degree 0 called as isolated. Here G is a isolated, and a vertex with degree 1 called as pendant. Here D and C are pendant. Now theorem 1, it is the handshaking theorem. So let G equals to VE be an undirected graph with M edges, then 2M equals to sum of V belongs to V, degree of V. So if we'll add all vertex degree, that will be 2 multiplication number of edges. So 2 into M equals to sum of all degree. And this formula applied to loop and multigraph also. Let's see one example. Example 2. How many edges are there in a graph with 10 vertices, each of degree 6? Each of degree 6, and there are 10 vertices. So 10 multiplication 6 equals to 2 into number of edges, 2 into m. So 2 into m equals to 60, m will be 30. So there are 30 edges, answer will be 30. Now theorem 2, an undirected graph has an even number of vertices of odd degree. So if we count how many vertices of odd degree, there are even number of vertices of odd degree in a simple graph. Next, definition 6, it's about adjacent indirected graph. When UV is an edge of the graph G with a directed edge, let this is a directed edge, this is U, this is V. U is said to be adjacent to V and V is said to be adjacent from U. The vertex U is called the initial vertex of UV and V called the terminal vertex, or we can say end vertex of UV. The initial vertex and terminal vertex of a loop are the same. Suppose there is a loop, then we can say its initial and terminal vertex both are same. Next, we will discuss in degree and out degree in a directed graph. If it is undirected, it's just degree. If it is directed, then there are two type of degree. One is in degree, another is out degree. Now definition 7, in a graph with directed edge, the in degree of a vertex V denoted by degree, here is a minus symbol, V is the number of edges with V as their terminal vertex, and the out degree of V denoted by degree plus V is the number of edges with V as their initial vertex. So we can say in degree means how many edges are coming toward V, or you can say in how many cases V is the terminal vertex. So there is a arrow toward V, that is in degree. And out degree means how many vertex are going out from V, means in how many cases V is the initial vertex. And in case of loop, in degree is 1 and out degree is 1. So loop means 1 in degree, 1 out degree. Let's see one example. Example 3, find the in degree and out degree of each vertex in the graph G with directed edge shown in the figure. This is the directed graph. Now we need to find in degree and out degree for each vertex. First I'll find the in degree. Now for vertex A to A and E to A. So for A, in degree will be 2. Now for B, A to B, C to B. So degree will be 2. For C, A to C, D to C and C to C. So for C, in degree will be 3. Now for D, E to D, B to D. So for D, in degree will be 2. Next for E to E, D to E, A to E. So in degree will be 3. For F, in degree is 0. So we found in degree of A equals to 2, in degree of B equals to 2, in degree of C equals to 3, in degree of D equals to 2, in degree of E equals to 3 and in degree of F equals to 0. Next we will find out degree. Out degree of A will be 1, 2, 3, 4. So our degree of A equals to 4. A to a self loop that will consider as in degree, also our degree. Then A to B, A to C and A to E. So our degree of A equals to 4. Then our degree of B equals to 1. Just one directed edge from B to D. Then our degree of C will be 1 due to self loop and C to B. So 2. Next our degree of D to E and D to C. 2. Then our degree of E, this self loop is 1, E to D is 1, E to A is 1. So it's 3. Our degree of F equals to 0. For F, in degree and out degree equals to 0. Now theorem 3, it's a variation of theorem 1, the handshaking theorem, that was about the degree. This is about both in degree and out degree. Let G equals to BE be a graph with directed edge. Then sum of in degree equals to sum of out degree equals to number of edges. There it was sum of all degree equals to 2 into multiplication of number of edges. Here sum of in degree equals to sum of out degree equals to number of edges. This is a variation of handshaking theorem. In today's lecture, I discussed adjacent, degree, in degree, out degree. In next lecture, I will discuss what is complete graph, what is biparative graph. If this lecture is helpful for you, please like, share and subscribe. Thank you.